Please welcome Mike Vinarsik.
Thank you for attending this session. Today we'll be talking about weaving the digital thread into the digital web, a presentation by myself and Amanda Kuhn's staff. We're both chief systems engineers at SAIC. And so if we consider product development starting from concept and going through disposal, this is a notional representation of the intermediate steps. But one of the problems we face traditionally is that we lose fidelity and momentum every time there's a handoff between activities, departments. This is caused by the air gaps, the transmission of specs, requirements documents, whatever it may be, the fact that we're presented typically an artifact to the downstream consumer without appropriate connections or linkages to the information we use to create it tends to cause problems, failures in integration, and other issues that we're all very familiar with. So digital engineering, digital thread, digital twin is this attempt to eliminate the air gaps that exist between these disparate activities. And so the future state of digital engineering, PLM and big data and failure logistics analysis kind of bridges this section of it, that let there be bomb moment, so to speak. The domain-specific analysis tools have typically existed in this more upstream portion, and the model-based systems engineering tools that I'm most familiar with typically live at this very front end, which again feeds in and informs all the downstream development. And so there's a transformation underway, moving from this bomb-centric view of products, where we don't have this holistic view of design intent, to one that's more architecture-centric, where this architectural representation of the system of interest spans and encompasses all the disciplines. It's transdisciplinary in many ways. And so the reason we have to do this is we have constant changes in customer needs, right? People want more sustainability, smarter systems, stability, simple, socially acceptable, safe, secure, scalable. The demands being placed on us as engineers and designers are just exploding. Plus, we have far more complexity in modern systems. I look at my dad's 1956 Packard. It was basically a moving steel box with some furniture in it. Compare that with a modern car and all the things it has to do in terms of crash, collision avoidance. I mean, there's a skyrocketing complexity in modern systems, particularly as more and more of the functionality is delivered by software instead of mechanical or electrical systems. And finally, we have much higher expectations for success. The days of tolerating oil leaks in your car and putting a drip pan under it are over, right? We just expect stuff to work right every time that we use things. So if we look at aircraft as a surrogate for complexity, this is just a graph of software complexity in military aircraft. You can see it's just exploding over time in terms of thousands of lines of code between the 50s and today. And the DoD understands this. Here's a great quote I love, that our current acquisition system is applying industrial age processes to solve information age problems. And I think that's true across any industry, whether it's medical, automotive, you name it, we're all facing the same challenge. Now, James Long, who's a fellow of the International Council on Systems Engineering, had this great law of conservation of SE. And it's the amount of systems engineering required for a project is fixed. It's set by the risk and difficulty of the program. So you really don't get to choose how much systems engineering is necessary to deliver it successfully. You just get to choose when you do it. Do you do it up front? Do you do it late during integration and testing? And you basically have to choose how impactful it is and how much it costs. And I'm a big believer that appropriate systems engineering up front minimizes this tax we have to pay on our development effort and increases the odds of program success. And I really love this quote from Hilary Solito's book on architecting systems. Architecting defines what to design, while design defines what to build. And I think that's the key statement here. And whether it's an agile development process or anything in between with big design up front, we still need a strong architecture that's developed at appropriate speed and fidelity. But that architectural glue is what helps all of our other development efforts succeed. Even in an agile case, I think having an appropriate level of architecture to communicate intent is critical for success. And so if we look at this slide and consider the digital tapestry, whether we're looking at the systems engineering V, different aspects of the digital thread, We have our system model that captures our design intent, often in SysML or some other modeling language. We've got the detailed design that we all know and love that typically resides in the PLM systems. And then we move our way up to the EBOM and bill of materials and our digital twins. But again, this architectural representation is this common thread that connects all of this disparate information and allows us to unify it so we're no longer siloed and stovepipe, but people are all drawing information from a common authoritative source of truth. And so systems engineering worries about behavior, structure, requirements, their relationships, and document-intensive systems engineering requires humans in the loop to try to sew all this together in their heads to integrate into a coherent understanding. But it's inherently lossy and labor-intensive, and it doesn't scale well to large modern cyber-physical systems. So we end up with these siloed, disconnected views. There's no guarantee of consistency. You often get things as PDF or Excel or disjointed artifacts, and it's hard to review this content thoroughly. But this is not a new problem. So if we look back at Apollo, they celebrated the 50th anniversary a few years ago, and back in the 70s, after they wound down the program, NASA published these Apollo experience reports. And this is one from Guidance and Control, which is arguably the unsung hero of the mission, right? If you weren't able to navigate to the moon and back and go from orbit down to the surface with the guidance and control systems, it would have been a non-starter. And look at what they wrote. So this is 1976. A failure analysis technique should be developed to assist in the identification of single-point failures. The Apollo method, in which many engineers must search diagrams for problems, is not altogether successful for complex systems. And I would argue that's an understatement, and think how much worse things are 50 years later with the exploding complexity of the software and everything else. This is with 60s fairly analog technology with early computing. Imagine what it's like today. And so again, this is not a new problem, and it's only getting worse. So model-based systems engineering is our attempt to solve this, and I would argue that competent model-based systems engineering is this foundation for this digital thread that we need to manage these complexities. SysML is the dominant language for executing these models, and a well-formed SysML model models the behavior of the system and the elements, and including how they collaborate with really good definitions of inputs and outputs. We understand the structure of our system, the components, the assemblies. We have the interfaces well defined with the flows and connections, parametrics that govern our behavior or properties, as well as the requirements. And there's even some level of automatic conformance assessment we can do to support automated AOAs and other things, analysis of alternatives. So there's just a lot of power at our disposal if we harness it properly. There's lots of tool chains we can build to make this happen, but federating this tends to be brittle and difficult to configure and administer. But if we don't use our models as the authoritative source of architectural truth, the entire digital thread is now at risk. And so in the beginning of 1.0 of MBSE, people were just recreating traditional artifacts and more sophisticated tools, and we didn't really have good config control or was limited or non-existent. But as we keep evolving, we now evaluate the use for every potential modeling artifact before we create it. What questions are we trying to answer? What technical debt or risks are we buying down? What's the bang for the buck that we get out of engaging in this modeling effort? And I was speaking on a panel earlier, and I said, I've never seen modeling make things worse, right? It usually exposes inconsistencies or flaws in the current architectural representation of requirements and other design intent. And so as we move forward and keep evolving the discipline, we have started to look at our methods and make sure we're being elegant, efficient, and effective, even if we're not being fully pure with the pure language. But we're trying to get this efficiency and effectiveness to get the fewest number of clicks to get to our uses, and how can we reuse things appropriately. And one of the key things is that we can write queries and infer a lot. I was speaking earlier today about a model my son did for a conference, showing how you can do automated failure mode effects analysis and show that function X participates in recovering from a failed state. So now you have understanding of the impacts that your various functions can have. And by reusing information and pulling things out of queries instead of manually setting them, we minimize these opportunities for inconsistency where things can drift and are wrong. As I tell my students, if the model's right and the query's right, the answer's right. And this lets us get to this complete synchronization between structure, behavior, and interfaces. So SAIC has released an example model and validation rules where it's given free of charge to the worldwide system modeling community. We're trying to improve model quality and accelerate training of competent modelers. It's got validation rules, customizations, documentation, videos, and it's freely distributable and licensed. We even include a model-based style guide and an example model based on the Ranger Lunar Probe, and it currently supports SysML in Magic Draw and as well as the Rhapsody tool suite from IBM. And so why would you want to use something like this? Well, there's too many options in the pure language. Just as English has lots of options, if you put a paper into IEEE, you have to follow their style. Having a style restricts the options available and makes sure everyone does it the same way. You only have to use a portion of the language, so training is quicker. New modelers can focus on representing technical content, not sorting out the best technique. Those choices have been made for them by the experienced modeling team that wrote the style guide, which lets you shorten your training. It's more effective. You can analyze the model because all the properties and relationships are where you expect them. It lets you federate more effectively because your model-to-model compatibility is improved. And you also can integrate more easily with a dashboard or PLM. So a key takeaway for anyone here is that a style guide is a key enabler to succeed with a model-based effort. Validation is also important because there's a lot of things we can test automatically, just as software community has their compilers and their error checking and unit tests. Automated validation of a system model lets us ensure consistency and completeness. We can test for gaps. You've defined a function but not used it, or you have a flow between two components but it's not formally mapped to an interface. There's an amazing amount of consistency you can get by squeezing a model down to no errors and no information warnings with a validation tool. And again, this lets us map our model to other data models. And so this gives us this consistent Rosetta Stone we need to be able to succeed. This is drawn from a paper I presented last year, and basically it shows you the errors that creep into system models without validation. So the blue line is a log plot of models done by professionals without validation. The two gray dots in the middle are students I had taught. When I validated their model, they had a slightly better or lower error rate, probably because I had taught them the sort of things to avoid. And then the orange dots are rookie students modeling with validation with effectively a zero error rate. So I hope this makes a compelling case why you would want to adopt some set of automated validation for your systems engineering models. So we're going to take a look now at a tool federation demonstration. And again, as I said, we made this model of the Ranger Lunar Probe that we provide as an example of how to do an architecture model. And so we used obviously a old NASA mission for this, and it let us refine our validation rules and style, and we give this away as part of the validation rule and style. And so we're going to have an example video here where we're going to look at how we could have a tool chain operating between the systems engineering modeling tool, Eris Innovator, and Jira. So in this demonstration, you'll see that we've synchronized the architecture with Eris. We're able to create issues in Jira and push software development information downstream into the tools that the developers will be comfortable using. And so, again, we've got a live demo here that was recorded to show this. So with that, I'll go ahead and let our AV team go ahead and run this integrated tool chain demonstration video. And again, this is all actual stuff being done in the tools. This is the sync works exactly the way we show it here. So please take it away. This is the SAIC DE system model example based on the Ranger Lunar Probe from the 1960s. It is a reasonably sized model, 26,000 elements or so, which is substantial and large enough to allow us to fully exercise various aspects of our modeling style. And this has been freely released to the modeling community along with our customization profile validation rules and a model-based style guide, and we encourage you to review this content. It's available at the links displayed on the screen. We will now analyze the model with the validation suite developed by SAIC that checks the model for conformance to the style guide, as well as ensures synchronization of behavior, structure, interfaces, and compliance with our style guide. So this model has 113 information warnings and 1 error. The information warnings tend to be related to missing interface mapping information, and these typically are a result of model maturity. However, the error is something that concerns us, and we should resolve that immediately. And if we look at this error, it's indicating that signal events must have a signal defined. So we can navigate quickly to the element that's throwing the error, and see where it's used in the model. So this is part of a state machine. And notice that this is the error. This transition does not have a trigger. And so we can go ahead and lock this element for edit. And we can either resolve it, or in this case, we will just delete it because it's likely a spurious transition. Now, to detect this manually would have been difficult. If we look at the model and we look at the state machine diagrams, which is where this was, there's a large number of these in this relatively simple system. This is the reason that we want to use automatic validation. It enables us to detect errors of this sort very rapidly, and it scales very well with large models. Running the validation suite on a model with 100,000 elements would not take that much longer. Again, a matter of moments to do reviews that by hand would take hours or days. The Ranger model represents both the logical and the physical architecture of the Ranger. So we have both the components that make it up at various levels of abstraction. We're interested in synchronizing the architectural information contained in our system model with other relevant tools. The demonstration today will focus on passing information about software functions to Jira and information about our bill of materials and structure to a CAD tool. In this case, we can look at the central computer and note that it has a variety of properties and interfaces, but it also has a large set of functions that have been defined that reflect both inputs and outputs. This is the sort of information we wish to pass directly to Jira to enable agile development to be in sync with the architecture. And so that gives you an understanding of what the architecture model looks like, and they will now look at a demonstration showing how this communicates with Jira and other downstream tools. So please go ahead and roll the next video.
This is the Mars Ranger model in Cameo that Michael just described. The objective is to communicate it to ARA's platform, subject it to enterprise-wide configuration control, revs and ECOs, and use it to drive specifics of the implementation domains. Like we said earlier, for it to become a connective tissue. Let me just make sure that there is no model information in ARAS. Oh, clearly, there isn't any. From within Cameo, I create a new rover model container in ARAS and populate it with the associated metadata. Note that this happens automatically in the sense that I did not have to manually interact with the ARAS platform. I did it from the Cameo's context menu. Next, I'll synchronize a specific SysML diagram in Cameo as the primary diagram to display in ARAS for this rover model. Again, I do it directly from a Cameo's context menu. Finally, I select a specific package with system elements that define operations to be implemented as physical parts or in software. This can be done in several steps or in a single batch. And now I'm synchronizing with the model container in ARAS all selected architectural elements and all associated relationships between these elements. This results in visual indications of the element status. Green dots indicate elements that were synchronized, blue dots elements that were not. Let's now switch to ARAS platform and see what the rest of the enterprise can see as a result. Clearly, there is a new model that I can access. Metadata contains information such as unique identifier, a GUID, name of the model, name and revision of the authoring tool, etc. The original Cameo file is preserved in the associated Vault entry, and I can see the diagram that I selected to be a default. Finally, I can examine all functional and logical items that were synchronized from Cameo. I will only see items that were included in the mapping dictionary. I now select one of these items to examine its metadata and to trigger a Jira issue from it. Let's quickly verify that there are no associated items in Jira at the moment. There are none. Back in ARAS, I can trigger creation of Jira issue from the selected system item. Here, I'm doing it for a single item. This can be done in batch or for a selected set of items. Switching back to Jira, I can now see a new issue to include in the software development process, and I can see all details associated with it as defined in the system model item. Let's now create a part in ARAS that is needed by the system model. This may be triggered from a system item like we just did for Jira. In this case, I'm doing it manually and will relate it to a system item a bit later. First, I generate a new part number. Since this is a Mars Ranger, I'm classifying it as an assembly. I then search for the related CAD structure already synchronized from a CAD authoring tool. In this case, it came from SolidWorks. Once related to the Mars Ranger assembly, this allows to browse the associated CAD document structure and all 3D views of the related geometries. I will also show that a bit later. For now, I can recognize the part by its simplified view in the form. Now, let's go back to Cameo and see if we can see parts defined in ARAS. Select BOM search with various filtering options, and ARAS returns a long list of parts. I will select the very first one, which happens to be an assembly. That assembly gets instantiated in a pre-selected package. And here's what the related multi-level part assembly looks like in Cameo. But what if I need a specific part, like Mars Ranger? First, let's open a part to logical block relationship grid. Then select the package that the part belongs to, and then do a part search, but now filtering on a specific name. Search returns the only matching part, and I instantiate it in the model. Here it is. I can now also see the Mars Ranger part in a relationship grid. A new relationship is created by clicking on the intersection with the appropriate logical block, and I synchronize that relationship with ARAS model using an appropriate context menu selection. As before, synchronization uses background services to the ARAS platform. Now I can do the same operation, but with requirements. First, the search for requirements in ARAS. And ARAS returns a list of requirements that match the search criteria, then selecting the one that is of interest, and finally instantiating it in a selected package. Here it is. Note that the operation also instantiated the requirement structure, a breakdown into sub-requirements as defined in ARAS. That saves a lot of time. This time, instead of a table, I will use a requirements diagram to create a new relationship. So first I open the diagram, then I add a physical block to the diagram, then I add the requirement that was just obtained from ARAS. And finally, I add a satisfied relationship between the two. These are all standard Cameo operations. And now I need to synchronize these changes with this model in ARAS. As before, synchronization is done via a specific context menu option, and by selecting either the requirement or the block. The last Cameo model change involves addition of a comment. The easiest way to do it is also using a diagram, and I chose an activity diagram in this case. I create a new comment and relate it to one of the elements on the diagram. To synchronize the change with ARAS, I use a context menu on the element within the diagram. So now we have three changes in the model that are synchronized with ARAS. Logical block to part relationship, physical block to requirement relationship, and comment related to a physical block. Let's go back to ARAS and see how the rest of Enterprise can see these changes. First, I will go to the collaboration area to see the notes from Cameo. Here they are on the right side in an interactive stream of notes. I can also open the synchronized diagram within the original comment. This is a static image. And I can add any graphical annotations right over it. Notes, pointers, red lines, etc. This does not modify anything. It is a graphical overlay. This is part of a visual collaboration functionality within ARAS. Collaboration info is retained as part of the data model, and can be retrieved at any time later on. Let's switch to the already open Ranger physical assembly item and go to the related requirements. This is the relationship that I just established in the Cameo model. I will now use a structure browser to see a tree of the related relationships. It is one of many options for structure navigation in ARAS. I can now see the whole assembly structure followed by the decomposition of the associated CAD documents and requirements. This allows me to generate an impact matrix should any of the items in the tree change. And finally, I will go back to the Mars Ranger architectural model in ARAS and open it again. I will now use an interactive graphical view to navigate the architectural breakdown of the system. Expanding individual model items allows to see the next level of breakdown plus other related items. These views are fully configurable for the task at hand. They also render data dynamically every time they are invoked. By navigating in various directions, I can find the item of interest. There is the Ranger physical part that we related using Cameo, and it points to the CAD model as well. Let's open it. It takes a little bit of time to navigate there. All right, here's the part that we defined originally in ARAS. Except now it is linked to the system model element in Cameo. I can now navigate the underlying structures in the context of the system model, where this system model is the connective tissue, including a full 3D rendering. This is the last step in the demo. The demo is based on a real and practical use case. Demonstration was put together using commercially available tools, Cameo, ARAS Platform, and Jira. We trust that you found it interesting and compelling. Michael, back to you.
And so I hope that gives you a sense of what's possible using ARAS and Jira and Cameo. And so now we're going to talk about one last step in this, which is looking at obsolescence. And so my colleague Amanda Kuhn's staff put this very short video together to show you a sense of what other insights you can gain from competent use of these tools. So go ahead and please play that video.
Obsolescence and diminishing manufacturing sources, material shortages, DMSMS plays a significant role in sustainment costs. Being able to select the right component early in design helps mitigate this issue. SAIC uses a special tool called IHS Market Parts Intelligence to help track and trend these DMSMS obsolescence, counterfeit, gray market, or high failure rated parts. This tool allows us to quickly look and compare risk for life cycle, environmental, and supply chain, while providing access to drawings and other pertinent documentation and alerts. We have found that by using ARAS Innovator Component Engineering module, we are able to access the required information and connect that back to our design and sustainment documentation. We key in the part number and are able then to start off a process for obtaining this information and connecting it inside of ARAS Innovator. For the sake of time, I won't start the whole process off, but will show you how SAIC has two processes that we can use to start investigation into component selection. The first that I'm showing is the manufacturer part request that starts when one begins to research the part on their own. You see that this request captures the data about the components themselves with descriptions, comments, and manufacturer information. Similarly, working inside an internal part request, we are able to show priority of the request, part number, and who it is assigned to. That internal part request will walk through our workflow process for approval, research, and results reporting. Those processes provide us with manufacturer part information that is stored inside of ARAS, in which we can now connect back to our system components. That is what I'm showing here. Our components reside in ARAS with all information, including how that part links back to the rest of the data in the CE module process. This can include alternate part information, manufacturer part information, and it can link back to the manufacturer alerts that we noted from the CE process. Looking at the manufacturer alerts, we are able to manage various alerts to include part failure notices, part supply chain issues, and end-of-life issues. SAIC has also created another way to link using specific DMSMS item type, which I will address shortly. Going back to the manufacturer parts here, SAIC also added an area to quickly determine available inventory so that our entire team, to include the design engineers and logisticians, can make a determination on component selection based on component availability. Our logisticians can set manufacturer alerts, and showing our SAIC created DMSMS item type, we can also quickly identify and compare components based on risks as identified in the IHS Market tool. We can also view documentation and declarations that we have found in the CE and IHS Market tool for quick access to data for each component. That data is all linked back into component part so that I don't have to tab through individual results. One can go directly into that part component and view alerts to include data from the CE manufacturer parts and alerts. As you can see, there are no alerts for this component. However, if I go to my other component, I can see the part alert that are now linked to the component. So this allows for collaboration between the design and sustainment teams and helps ensure designs are selected based on data to include DMSMS, obsolescence, and other part issues.
So thank you. So that was an example of Amanda showing what it's like to, like in this case, look for a new receiver for the Ranger. And so again, these were all live demos in the tool showing you how they actually work. And so I'll leave you with these thoughts. And again, thank you for your interest. A competent, well-formed system model in SysML gives us this rigorous, unambiguous representation of our architecture at whatever level of abstraction is appropriate, from enterprise down to detailed pinouts. The queries, validation rules, and derived work products ensure that any stakeholder gets valid information. It's this authoritative source of truth that we can rely upon. And the competent modeling gives us rigor at the speed of relevance that helps us meet our customer needs. I hope I've made the case to you that automatic validation dramatically can improve model quality, facilitates other analyses, and enables information to be encoded in such a way that it's available and relevant to everyone else participating in the digital thread. And this synchronization of these federated tools driven by our authoritative data sources really can improve collaboration and communication across all disciplines. So thank you so much for your interest. I hope that you're enjoying ACE, and we look forward to having any further dialogue with you. I point out that Amanda has another presentation later in the program, and if you're interested in seeing more of her work, feel free to tune in. Thank you so much, and have a great day.